What is present in this location is what will happen to it. So you moved it down. For example, if it was here in the middle and you moved it down, then it's just this location. The location remains. The place where you will apply the signal is exactly where it will occur. Okay, if you say, you will give your RF pulse here, then your location will change. So, where is the RF pulse applied? It is in the gradient that determines the selected slice that will be excited on your z-axis. Now, this gradient can be controlled. I have point P, and this gradient can be small or more steeper. What does more steeper mean? It means you have increased the variation between each point and the next. For example, this is your gradient, which is neither too large nor too small. If you make it more steeper, it means that at that time, you have increased the variation between each point inside the magnetic field, which will give you more resolution. This means that the protons next to each other are in a very small space, and each one of them rotates at a different speed. So you can achieve this especially with a small slice thickness image. If you choose a small slice thickness in imaging, you want a higher resolution, so you need to make your gradient steeper to provide you with more resolution. This allows adjacent protons to spin at different speeds, giving you higher resolution. This is what happens in slice selection with small slice thickness. That's why on 0.5 Tesla machines, they tell you that if you work, for example, I want to walk before I go down to a slice thickness, for example, 1 meters, 2 meters, or 3 meters. So I adjusted the RF pulse and said I want 3 meters, but I can't go down more than that. The technician says, no, doctor, I can't give you a 3-meter image on the machine. The machine is hanging because the gradient is limited, especially with this machine. It can't do more steps to increase what you requested because it needs to adjust for your image. As you can see here, so, as you know, we have made a distinction or difference. We talked last time in our previous discussion, and I brought up that I have the image and you have the pixel, which has its own unique characteristics. So, what do you want to do? You want to differentiate between the pixels in the y direction and the differentiation between the pixels in the x direction. So you apply two gradients, one in the y direction and one in the x direction. Which one is in the y direction, doctor? We mentioned last time that it was the phase encode gradient, and which one was in the x direction? It was the frequency encode gradient. So we apply the first gradient in the y direction to differentiate the precision frequency between the protons in this pixel, this pixel, this pixel, and this pixel. What does it do? It applies the phase encode gradient. What is that? You don't just apply it once. You apply it at several angles depending on the size of your matrix. For example, if you are using a matrix size of 256, what is your phase encode gradient? 256, meaning it changes the gradient at different angles, with each angle responsible for reconstructing one line in your image. Now let's see this in detail. Here, this is the gradient that will be applied to make the protons rotate at different frequencies. So, one will lead the others, and then they will all return to the same speed. However, the autophase will create a difference in phase between the protons present. Let's pay attention again to how the gradient is applied. Initially, they were all rotating together, but when the gradient is applied, the frequency changes. So they keep giving you a signal at different times, even if they give you the same signal with the same frequency, but at different times, so you can receive it. This means you have differentiated between the pixels present on the y-axis, because there is a difference in time and a difference in the phase of these signals. Now, pay attention to the phase being applied. We said, look, I create the first phase and then a phase with a higher degree each time. You increase the gradient on the y-axis. Why? because I will use the first one to reconstruct the first line or the first column in the matrix. I apologize. The first line I have or the first row in the matrix. The second one is the second row, the third one is the third row, and so on. So if you apply your gradient on the y-axis at the same degree, they will all give you the same time. Therefore, the first one gives you a time, and the second one wants to increase the degree of the gradient to give you different times and other different times. As you can see here, the signal is coming to you here, for example. In this image, at a certain time when I increased the gradient, what happened? The signals here showed differentiation between the times you are receiving. Now, when I increased the gradient, the times of the sine waves coming to you became completely different. So why do you decide to do this operation? As I mentioned, with your matrix, every stepping or every degree of the gradient or every angle of the gradient you apply is to reconstruct one line from your image, right? From your matrix, here is the frequency encoded gradient, which differentiates between the pixels present in the row, which is at the level of the x-axis. When you apply the gradient, the same idea changes their frequency. They were all rotating, and then when you apply the gradient, you find their speeds different in frequency encoding gradient. So why do you use it? You use it to differentiate between the pixels present in the x-axis, so you have each pixel giving you a signal at a different frequency. In different times, you were able to obtain this signal that came to you in the time domain, and you can transform it to the frequency domain. After that, you can store this entire signal in what is called k-space. Now, in the phase encoding gradient, what was I doing? I was saying different degrees. Here, for example, the stepping of the gradient is low, while here it is high, meaning you are continuously applying the gradient. In the y-axis, once here with one angle, then with a second angle, and then with a third angle, I increase the stepping or increase the degree of the gradient. Every time I increase this stepping, it's as if I'm increasing the resolution, as if I'm increasing the difference in the phase of the protons coming to you. Every time you do this, you obtain a signal. This signal starts to change in its frequency and its phase. This change means you begin to receive a signal. This incoming signal has a different frequency and different amplitude because you converted time into frequency. So now, the time that was coming to you has been transformed from the time domain to the frequency domain. The amplitude represents the magnitude of the signal, the strength of the signal. The signal is coming from high magnetization, or it comes from a strong magnetic field, whether longitudinal or transverse, or it comes from weak longitudinal or transverse fields. It will come to you with weak amplitude. So you have two things, a high frequency signal and a low frequency signal. The low frequency will always be associated with the high amplitude signal. If we remember the topic of line pairs, it will always be related to that. When we increase the line pairs present per millimeter, it gives you high frequency. And with the increase in high frequency, your amplitude decreases. The same idea applies to the signal that you are receiving or that you are receiving from the pattern. This signal comes like this. Look at your movement here. This is a completely ordinary image. I have taken a line profile of this monkey. What do we have in this image? I have two curves like this. This curve represents the amount of values or changes in the pixel values at this line level. In this area, which is very close together and lacks variation, you will see how the curve looks. Your curve is in the time domain or space domain. I call it the time domain. or space domain, and I convert it here to the frequency domain. You will find signals from your image that have high amplitude. The area in the middle here is high amplitude and low frequency. I apologize. Yes, high amplitude and low frequency, and this has high frequency. There is a frequency difference, and at the same time, low amplitude. The area in the middle here is represented by the sine wave, you see, and this area is represented by the peak, and the point here, which has high frequency. This always represents things with high resolution. High resolution, let's go back to this beautiful shape. Excuse me, sir. This image is moving. I can't stop looking at it. Yes. The image that you see moving, is everyone okay? You all see the movement? Everything is fine? There are no problems? I am in this exact area. Is it this area or that area? Which area do you feel is noisier? This region or that region? I mean, is this area noisier for you, and does it have higher details, or is it that area? Have this thought. There's more noise outside. The more noise there is, the higher the frequency. Higher frequencies mean that the variations in pixel values are numerous, meaning each pixel has a different value from the adjacent one. The differences in pixel values in that outer area create high frequencies, which is the high frequency region. Meanwhile, the area in the middle is more homogeneous. The changes in pixel values are not high. You have a large white area and some gray, so the changes in pixel values are few, giving you a signal with high amplitude. At the same time, there's low frequency. This is what happens in the image of the mirror, folks. The image of the mirror, or any imaging modality we've talked about before, relates to the same concept and meaning. You have a signal coming in that is high frequency and a signal coming in that is low frequency. High frequency always represents noise. The low frequency always represents what? Your object that you are imaging is the same story, so the low frequency represents the image itself and the object you are imaging, while the high frequency represents the edges and margins of the images, indicating areas with noise. So high frequency is always for the edges and noise, while low frequency is for the object you are imaging. But what's the difference? It's in the amplitude. The amplitude of the object you are imaging is high, so low frequency has high amplitude, and the other one, high frequency, has low amplitude. Okay, come here, look here. What is this again? All right, come here. Now let me explain this. Look, this is the RF pulse that you apply, which is the 90-degree pulse. Then you apply the slice selection gradient. After applying the slice selection gradient, you apply the phase encoding gradient, which we discussed to create the y-axis. Now, leaving those 2 points aside, I will explain them in a bit. But after applying the phase encoding gradient, you apply the frequency encoding gradient while you are reading and recording your signal. The frequency encoding gradient is turned on and off repeatedly, allowing you to take the first line, then go back and repeat your signal, giving a new RF pulse and repeating the sequence to take the new line, the third line, and so on. The frequency encoding gradient is only active during the signal recording. Now that I have the signal, focus with me. This is my K-space. K-space is where the raw data is. I start by filtering the K-space. When you filter the K-space, you find that the image starts to form, with the point in the center and the edges. The white spot in the center represents the low frequency and high amplitude. It filters the low frequencies, which are the low frequency and high amplitude at the center. Frequency and the periphery is responsible for the high frequency resolution at the edges and low amplitude for storing the data. The inverse Fourier transformation retrieves your image by storing the data in the frequency domain. It converts the information taken in the frequency domain back to the space domain, which means location, representing your actual image, or your time domain, which is this image. Each pixel has a frequency and an amplitude, and it starts to revert to your image through the inverse Fourier transformation. Now look here. I will start with my K-space. This is the phase encoding gradient, which will apply this amount of gradient. And this is the frequency encoding gradient. This is on the x-axis. And this is on the y-axis. Now I will start filling this line, and then I will move to the next line, and then the next line, and so on. Each gradient from the phase encoding gradient fills a line, and each angle from the phase encoding gradient fills a line. Look closely. The first angle leads to the second, third, fourth, fifth, and sixth. Look, focus with me here. You will find the strength of the magnetic field. Here, the gradient will start to decrease, 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 returning from positive to negative, and then it goes back in the opposite direction. Look at the first line, the second line, it goes down. Each time the phase encoding changes and starts to fill a new line. The image starts to form for you. Look, as soon as it starts to fill in the area of the center, the image begins to clarify for you. At first, it gives you the margins, but the edges are the areas that have high frequency. Then, it starts to show you the areas that have low frequency and high amplitude. In the beginning, the emergency situation gradually reveals the initial segment of the image. As time progresses, you will start to notice the subsequent parts of the image appearing below the initial one. This process is akin to the experience of observing the K-space, which is a concept that might be new to you. Take a moment to focus your attention here and observe how the image unfolds in a sequential manner, providing a deeper understanding of the K-space phenomenon. Look at this point. It's like it's moving. Here in the middle, is this low frequency or high frequency? This is low frequency with high amplitude. Now look, as it moves towards the periphery, what will happen? The more it moves to the edge, it will start to give high frequency with very high responses. Every large variation here is represented by pixels, but it has amplitude. This, folks, is our K-space. This is our K-space. All right, here is the image. If you took a part of the K-space and said, I want to do a reconstruction of the image using, for example, the center, what do you expect the image to look like before we see it? If you only took the center from the K-space, will this image be smooth or rough? Does it have details or not? Let's focus on those who said it is smooth. Why did they say smooth? And those who said it is rough, why did they say rough? It's beautiful. But there's a point. Right now, I'm going to take the data in the middle. This data will give you contrast. But how will your resolution be? Will you be able to achieve low edge resolution? That's what I'm talking about. Look at how the image looks here. I'm just going to take this part and look at the image. Okay. Is that it? This is what you will get. The image has become very good because it has always lost, as I tell you, a little bit of noise doesn't hurt. It means that the noise, when present, should give you a detrimental effect, but it will affect you in terms of the image. Come here. Let's reflect on this. If we only take the peripheral outermost edges or the peripheral area or region that is present in the case, we will use it. But unfortunately, sorry, it is just the H that will appear with you. And the features of the true image that you actually want will ultimately disappear. So it shows the image in this way. All this talk makes it clear why the doctors found the images to appear this way. Okay? This is the answer. The image appears with us in the end. Well, that's nice. These are the existing gradient forms that operate with the slice selection gradient. And this is the variation of our gradient, for example, in the y-axis, like the z-encoding gradient, or in the z-axis, similar to the slice selection gradient. All right, let's talk about how we have entered into a special encoding event to visualize what is happening. And we will continue discussing the T1 sequence, T2 sequence, and protodensity sequence, along with the sequences related to them. Up to this point, the discussion is quite understandable, or are there any issues? All right, thank God. Now let's go back to the story of longitudinal magnetization and transversal magnetization. Your RF pulses caused excitation, which made the protons that had a net magnetic force in the z direction move into the transverse plane and appear in a certain shape. We all mentioned this last time. We said that the protons, instead of being out of phase, became in phase and gathered together. So, we have transversal magnetization and longitudinal magnetization. Last time we talked about this. Let's take a look at something together now. What is this curve? This curve represents when you stop with the RF pulse, it starts to return, specifically in the z direction. This return is what undergoes relaxation. So how does this relaxation happen? What does this mean? Relaxation or longitudinal magnetization increases and returns depending on the loss of its magnetic force, meaning the loss of protons' magnetic force related to the lattice, which is the environment around them, namely the surrounding molecules. The process of losing and transferring this magnetic force causes the relaxation to be either fast or slow. For example, the relaxation of water is slow, unlike that of fat. This is due to the structure of fat and the structure of water. The structure of water makes the process of relaxation, or the loss of magnetic properties, or the loss of the magnetic signal it received, or the RF pulse it received, slower than that in fat. I call it spin lattice relaxation. This is for whom? For me, it's longitudinal. The return of the magnetic field to 63% of its value is what I call the T1 constant. So the T1 constant is the relaxation to 63% of the magnetic field value. I mentioned that I have different tissues fat and water. Fat returns quickly while water takes longer. This is the time, and this is the mz that follows the longitudinal magnetization. Therefore, I choose the time to record the signal where there is a difference in magnetization between fat and water. Fat is above and water is below. If I choose a time that is too far apart, there will be no difference between the two, so the signal will not show any difference between fat and water. I need to choose a short time. A short time to ensure there is a difference between fat and water in the mz. In this case, I choose an image based on the T1 difference, so I call it a T1 weighted image. All right, let's focus together. I am now there is fat and water. I applied the RF pulse, and both go into the transverse plane in the X and Y directions, right? Thus, the transverse behavior of fat and water is the same. When I start to remove the RF pulse, relaxation begins and they return. When I remove the RF pulse, relaxation occurs, and I need to know which one will return faster. The fat returns faster than the water. Now, if I stop and measure the signal, which one will be more bright? Great. Measure the signal for fat. And water returning in the Z direction now, returning to the Z axis. I can't measure my magnetic field while it's in the same direction as the node. I can't, right? What to do? You apply another RF pulse at 90 degrees. The RF pulse will lower the fat and lower the water, tilting the yellow line 90 degrees, so it is here. And the blue line, the water, is also tilted 90 degrees, so it is here. The difference between the yellow line and the blue line, or fat and water, will remain. When you come to record the fat signal, it will be more bright than the blue, the water. Why did you do this? Just to change the direction of longitudinal magnetization from being in the Z-axis to being in the X and Y axis. Is that understood, doctors? All right. So the time between, the first is a false.